Hello friends, today we start with the topic called as the finite automata. In our last lecture we have seen the Chomsky hierarchy. In the Chomsky hierarchy we have seen the type 0 grammar, right? What was the type 0 grammar? Type 0 grammar was a regular grammar. And as you know that every grammar generates a language. So this regular grammar is also generates a language. The language known as a regular language. And whatever the language generated by this, we are having a finite automata. And this finite automata is a language acceptor, right? This is a regular grammar which will generate a language called as a regular language. And the language generated by this grammar, we are having an acceptor called as a finite automata. So this finite automata, what is the nature of this finite automata and how this finite automata works? See, for example, suppose we are having one input tape, and in our input tape, the input symbols are there, and to read this input symbol, we are having a finite automata. The working of finite automata is like this. This is our state indicator and this is my tape head. And the finite automata reads only one character at a time or read only one symbol at a time. For example, here, this is my tape head which is about to read this 0 input symbol from the input tape, and my current state is say Q0. When my tape head will read this particular symbol from the input tape, what will happen? My tape will move towards right by 1. That means what? The finite automata ka tape movement is always move towards right by 1, and at that time the state may change from Q0 to some other state. For example, suppose if machine reads a 0 from the input tape and my current state is Q0, so my Dell function says that if I am going to write it down the state transition function, my current state is my Q0. What is my Q0? Q0 is my current state. Q0 is my current state, and what is my current input symbol? Current input symbol is the symbol where at that point my tape head is pointing towards, right? My tape head is pointing to 0, so this 0 is my current input symbol. So 0 is my current input symbol. Right. After reading this current input symbol, what will happen? My tape head will move towards right by 1 to read the next character. Right. So the Dell function of this finite automata is Q0 current state and the 0 is the current input symbol, and after reading this current input symbol, it will change the state. Suppose, for example, if it's change the state from Q0 to Q2, so this Q2 here in this example, I'll say that my Q2 is next state. Right. That means what? The working of the finite automata is it will stay at one state, it is going to read some input symbol from the tape, and after reading this input symbol, it may change the state. Sometimes it is not mandatory that you have to change the state. Sometimes it may remain in the same state, or sometimes it may change the state, right? So whatever the change state is there, that state will act as the next state. And this is my Q0, Q0 is my current state here, 0 is the current input symbol, and Q2 is my next state. So this is the overall working of my finite automata, right? And here after reading the current input symbol 0, my tape head will move towards right by 1 to read the next character. That means what? The finite automata, the tape head movement is always towards right by 1. So it is only move in only one direction, that is from left to right. So this is what my finite automata is. Right. So this is the overall the mathematical model of my finite automata. But here we'll see that what are the various finite automata we are going to study in this syllabus, right? The finite automata, here we are having a finite automata, and the finite automata will see that there are two types of finite automata. First finite automata is called as Nfa, and the another type of finite automata is called as a Dfa. Right. So what is difference between these two, Nfa and Dfa? Whether both are same or there is some difference between these two. But before that, we have seen this mathematical model of finite automata. Here we have got some idea what are the various states are there, right? So we are having this Q0, Q1, Q2 and Q3. What are those? These are my states, right? So I'll just say that this is my set of states. So here, if I say that I'm having some Q0, Q1, Q2 and Q3, I am having this 4 states. I have made as a set of those states, and I have denoted this set of state as a Q here. So I'll just say that Q is my set of, or I can say that it's a finite set of states, right? What I'm having the other things here in my mathematical model. In this mathematical model, I'll find it out there are some input symbol as well. That means what? In this finite automata, this input symbols I need to consider. So I'm having a string which consists of only zeros and ones. So I'm working on which sets? I'm working on the input set or input alphabets. It is called as it is a set of zeros and ones. So that is denoted by, I'll just say that it's a sigma, right? And here you will come to know that I start from one state, right? And that my starting state was what? Q0. So here I'll say that my Q0 is my initial state. So every finite automata should start from one state, and that state is called as the initial state. So here I'll just say that my Q0 is my initial state here. Q0 is an initial state. Right. So what should I do? Here after this, I'll come to know that after reading one input symbol, I have told you as this I have at the Q0 state, after reading this 0, it is moving from Q0 to Q2. That means what? The state is changing, right? And the way they change the state, it is denoted by del. And del is what? Del is called as the state transition function, right? That means what? It will show you what is your current state, what is your current input symbol, and after reading that current input symbol, where your machine lies, right? And what is the next state of your machine, that is denoted by del. So you must know the del as well. The del is called as my transition function, or I can say that it is my state transition function. Right. So this is the first tuple Q, sigma. I have got Q, I have got del. What about the last tuple, right? So how do I come to know that whether my finite automata is accepting this particular language or not, right? What it says that I'm having a string which consists of 0, 1, 1, 0, 1, right? This is my complete string. After reading the complete string, after reading this last one, I'll just check it out. What is my current state now? After reading this 0, if my current state is, say, in this scenario, if it is a Q3, and if I say that Q3 is my final state, and after completion of this reading process of my input string, and if my current state is my final state, then I'll just say that this particular string is accepted by this finite automata. If my string reading process is finished, and if my finite automata lies in one of the state which is called as a non-final state, right, and that particular string will be rejected by this finite automata. So finite automata is not going to give me any output, right? What it gives me, only this, whatever the strings your finite automata is going to read. After reading the string, my finite automata will give me the one answer only, whether the string is accepted by this finite automata or rejected by this finite automata. And this decision, this finite automata will take based on the current state only, right? When after performing the reading operation, and at the current state, if I find it out, my current state is a final state, then the finite automata will accept the string, otherwise the finite automata will reject the string, right? So we got 4 different tuples. Q is equal to Q0, Q1, Q2 and Q3. This is, I called it it's a finite set of states. This is sigma is equal to, it is the set of strings which consist of zeros and ones. So I'll just say that this is my set of input alphabets. Q0 is my initial state. Del, we have seen that how the del works. It will take the current state, current input symbol. After reading this current input symbol, it will go to the next state. That state transition is denoted by del, right? My last tuple, I'll just say that f, instead of f, I'll just say that it is a set of f, which is called as it is a finite set of final states. So why I've used here set? Because in my finite automata, I do have only one initial state, but in the finite automata, it may consist of more than one final states. So that is why instead of one single set, I'll just say that it is a set of final states. So these are the 5 tuples of finite automata, right? So whenever I define the finite automata, this finite automata is defined by these 5 tuples, that is Q, sigma, del, Q0, and this is what? Set of F. This is the mathematical definition of my finite automata. Whenever any finite automata is given, the finite automata will be based on these 5 tuples only: Q, sigma, del, Q0 and F. So here we have seen that the finite automata, there are 2 types of finite automata, as I have not yet differentiated between these two. This Nfa stands for non-deterministic finite automata and Dfa stands for deterministic finite automata. So what is the Nfa and what is the Dfa? In Nfa and Dfa, as both are the type of finite automata, so both the Nfa and Dfa is consist of these 5 tuples. So what is the difference between these two then? So the difference between Nfa and Dfa, both are having these 5 tuples, but the difference is the way of they transit the state, right? That means what? The Dell function. Only based on this Dell function, these 2 finite automata will be differentiated from each other. So what is the Dell function of Nfa? If I say that this is my Nfa ka Dell function works on the current state, and this is what the current input symbol, that means what? It will take the current state and the current input symbol and it will give you the next state. But as it is an Nfa Dell function, so my next state is not only the Q, it is what? It is a 2 raised to Q. What is 2 raised to Q? 2 raised to Q is a power set of states. What does it indicate? It indicates that suppose I am having a Q. Q is what? Q is a finite set of states. If I am having a Q which consists of 2 states only, Q0 and Q1, right? So if I want to find it out, the power set of this state, so 2 raised to Q, that means Q is a number, right? How many states I do have right now? I am having 2 states, right? And 2 raised to Q, 2 raised to 2, that is 4. In my power set of this state, power set of states, so what I am going to get? My first state is what? 5, second state is Q0, third member is Q1, and the fourth member is combination of these two, Q0, Q1. So the total in the power set of states, I am going to get the 4 states, right? What does it mean? It means that in my Dell function, if I am going to read one input symbol, if Q is I am at the current state Q, after reading this current input symbol, it may go to the next state, and the next state ka member might be, it may be 5, it may be a Q0 itself, it may be next state called as a Q1, or it may have Q0, Q1. That means what? It may have more than one transition on one input symbol. If it is like this, then I'll just say that this particular finite automata is a non-deterministic finite automata. For example, I'll just take one example here. This is my Q0 and this is my Q1, where Q0 is the initial state. This is the standard notation to denote the initial state, and this is the standard notation to denote the final state. Suppose there is a transition on A from Q0 and there is one more transition on A from Q0 to Q1. What does it indicate? If I am at the current state Q0 and the current input symbol is what? A. After reading this A, what is my next state? Right, my next state is what? From this Q0, if I read this A, I'll come back to the same state again. That means what? Because there is a self transition, so I'll just say my next state is a Q0. But there is one more transition on the same input symbol, that is A from Q0. So I am going to get one more transition, that is Q0 comma A. I am going to get what? Q1. Means what? On A, I am having more than one transition, that is one is Q0 and other one is Q1, right? So this is that particular member where I am going to get the transition on A. That means what? This Nfa transition says that if you are having more than one transition on one input symbol from any state, then it is called as Nfa. And if I want to draw the Dfa transition table, Dfa transition says that del Q into sigma, it gives me Q, right? And here, why it is so? And what is the difference between these two? What it says that this is my current state, sigma is my current input symbol. After reading this current input symbol, I should go to the Q. And what is Q? Q is a set of states. And where, how many states I do have? I have only two states, Q0 or Q1. That means what? Here this Q will be replaced by either Q0 or Q1. What does it indicates? It says that in DFA or in a deterministic finite automata, on any state, on one input symbol, you have a unique transition, right? So this is the major difference between NFA and DFA. So here, I just wanted to give you one relation between NFA and DFA. What does it says that if I draw a Venn diagram for this NFA and DFA, here I am going to write it down. This is my, if I say this is my DFA and this is my NFA. From this transition diagram, I can conclude one thing here. Every DFA is my NFA, but not every NFA is my DFA. Right? As I have said that Dell transition is 2 raised to Q. If I am having this NFA, if any NFA or any finite automata is having a multiple transition on the same input symbol on any state, that is an NFA. But that I cannot call it as a DFA. But any DFA, if I draw any DFA, definitely that is my NFA, right? So there is one standard procedure and you can say it's an algorithm. So we need to convert the NFA to its equivalent DFA. Thank you.